In this video, I will use calculus to apply the geometric series to generate power series for other functions. This is the second video in a series of two, where the previous one I already did up here, and the previous one uses only algebra to go from geometric series to power series for other functions. In this video, I'll also use calculus, meaning derivatives and integrals. So this is a geometric series, and the key is that the form of the closed form is 1 over 1 minus x. In the previous video, I showed how you can use algebra to convert a given function into the form 1 over 1 minus something, right? That block of something. And once you have that in that form, then you can use a power series and take that block, the y, whatever block of y is, and plug it into the power series. And examples of algebraic skills that you needed that I showed in the previous video includes things like if you have a plus, then change it to a minus of a negative, and then plug it in to the power series. And sometimes if there's a negative, something to power nth, you separate out the negative one to power nth. Another example is to factor out the number to make it 1. A third example from the previous video is I have this big rational function, and I have to use partial fraction to break it out, and then within that, I separate them into two separate geometric series, and then I sort of combine them together. And so those are the algebra skills. What I'm doing in this video is I add on to it derivative and integral. So add on to it calculus skills. I take the given function and I relate it with the form 1 over 1 minus something, where the relationship between them is some kind of derivative or integral. All right, let's start with our first example, ln of 1 plus x. Now, those of you who are taking a calculus class with a calculus textbook, you should know that in most textbooks, there is an actual formula for this, for the power series of ln of 1 plus x. Let's pretend we don't know that formula. What can I do with this? How do I make this into 1 over 1 minus something? Well, I know that the derivative of ln is 1 over x. So the derivative of ln of 1 plus x is over 1 plus x, and that is of the form. So now I know that. Let's try that. Let's fill in the details. If I take the derivative of ln of 1 plus x, I'll get 1 over 1 plus x, which I can rewrite in the form 1 over 1 minus negative x. That way is in the form of a geometric series, and I can apply the geometric series to this. Negative x to the power nth, where the convergence is that quantity less than 1. Negative x to the nth is the same as negative 1 to the nth times x to the nth. So most people prefer to write it like that so that you can see that it is an alternating series. And negative x absolute value is less than 1 is the same as absolute value of x less than 1. So this is the power series of the derivative of ln of 1 plus x. And now I want to get back to ln of x. I should take the antiderivative both sides. I should integrate both sides with respect to x. If I do that, then on the left, I have ln of 1 plus x. Then on the right, I have the integral of a power series. Well, the integral of a power series is the integral of a sum, well, an infinite sum, but still just a sum. So I think I should be able to just integrate the terms of the sum. And it turns out that, yes, I can, but I'll talk about that theory in a minute. Right now, I just go ahead and switch the integral to the inside. Negative 1 to the nth doesn't have x in it, so it's just a constant as far as the integral is concerned. I factor it out. And the integral of x to the nth is x to the n plus 1 divided by n plus 1. And the whole thing plus c. And this is ln of 1 plus x. And the interval of conversion is still the same as before, so it's still absolute value of x less than 1. Here's my answer so far, and I know I'm not done yet because I have that plus c that I need to take care of, so I have to find the c. And I find the c by fixing a specific value of x and then equate the two values from the left and right. A good convenient value of x is to set x equals 0. Then on the left-hand side, I have the ln of 1 plus 0, which is ln of 1. And that is 0. And therefore, on the left, I have 0. And then on the right, I have 0 to the power n plus 1. All of this is just 0. And therefore, c is equal to 0. I copy all of this down with 0 in for c. And the convergence is absolute value of x less than 1. I'm practically done, but here's something that people do with power series. When you write power series, you like to write it in the form x to the nth and not x to something else. I mean, unless you have to deal with odd even, right? You have seen those formulas for sine and cosine where you want it to be 2n plus 1 or 2n to specify that is odd power only or even power only. Where the power isn't specifically just odd or even, but all integers, you want this number to be n. It's just a preference. So let's do what we call shifting the index. Now, I have a separate video on shifting the index, but that video is not just on shifting the index, it's shifting index and doing a whole bunch of other things in differential equations. So check it out above. You only have to watch the part about shifting the index. It starts at 7 minutes and 25 seconds. Start watching there. But I will show you how to do it here too. So we want this power of x to be just n. So for the moment, I'm going to write a capital N. Then I want capital N to be equal to little n plus 1. If capital N is little n plus 1, then little n is equal to capital N minus 1. When little n is equal to 0, then capital N is equal to 0 plus 1, so capital N is equal to 1. Therefore, I can write my series as capital N from 1 to infinity, negative 1 to the little n is capital N minus 1, x to the little n plus 1, that's now capital N. And then the denominator is little n plus 1, which is capital N. So now I have my series in the form of x to the power n. But capital N is just a dummy variable. It's just the index of the series. X is the variable in this function. So it's an actual variable. N is just what we call a dummy variable. It's there so we can count from 1 to infinity. It doesn't have to be n. It could be k, j, or little n. So since it's a dummy variable, we can rename it again as little n again. So I can rewrite this as regular n from 1 to infinity. The radius of convergence is 1, and this is my ln of 1 plus x. That's the answer. It's exactly the same as the formula in your calculus book. So I've successfully derived that formula using the geometric series without having to go through the original formula for the Taylor series. All right. Back here, we did something fancy and also a little questionable. We arbitrarily moved the integral sign from outside the sum to inside the sum. And I arbitrarily moved it in. And I sort of justify it by saying that, well, the integral of a sum is the sum of the integral, right? We knew that from Calc 1. But that's only true if it's a finite sum. We started with the integral of the sum of two functions is the sum of their integrals. So we started with just a sum of two terms. And if we generalize it, we can only generalize up to some kind of finite number of sums. This is an infinite sum. The power series is an infinite sum. We don't know if that's legit. We don't know if we're allowed to do that. So in reality, we are only allowed to switch the integral from outside the sum to inside the sum if there's a mathematical theorem that allows for that. And lucky us, yes, there is. And indeed, there is a theorem that allows us to do that. It goes like this. If a function is a power series, can be expressed as a power series, and it is absolutely convergent in the interval absolute value of x is less than some radius r, then we can take the derivative of a function by differentiating term by term. The derivative of the function is the same as the derivative of the power series. So far, so good. And what's useful about this theorem is that it says that we can take this derivative here and we can move it inside. We can do it one term at a time. And it would still be equal to the derivative of the given function. And the same thing with the integral. The integral of the function is the integral of the series. Yeah. And we can also move the integral inside and integrate the series term by term. And all of this will still work for the same convergence interval of convergence. So we have this theorem, and this theorem is based on a result in real analysis called the uniform convergence theorem. I'm not going to prove this theorem. I'm just going to be happy that this theorem exists, and I'm going to use it so that I can differentiate and integrate power series term by term. All right, let's do another example. Find the power series for arctangent. Again, this is a known result. The formula for the power series of arctangent is shown in almost all calculus textbooks. But again, we're going to pretend we don't know that, so we're going to derive it now. I know what I'm trying to do. I'm trying to relate arctangent to a function of the form 1 minus something. And I start thinking in terms of, okay, what's the integral of arctangent? What's the derivative of arctangent? Is there anything somewhere there in the integral or in the derivative that looks like this form? So as soon as I start thinking of all the formulas I know, then I remember that the derivative of arctangent is 1 over 1 plus x squared. And this one is of the form 1 minus something, and therefore I can apply the geometric series to it. In geometric series form, it is negative x squared to the nth, like that, where the convergence radius is minus x squared absolute value is less than 1. I'm going to work out the algebra here. And absolute value of negative x squared less than 1 is the same as absolute value of x squared less than 1. Then I take square root both sides. I have absolute value of x is less than 1. And this is a derivative of arctan x. So now if I want the power series for arctan, I have to take the integral both sides, dx. And I also know, thanks to that theorem, that I can do this term by term now. On the left, this is arctangent x. And on the right, I know that I can integrate term by term. Negative 1 to the nth doesn't have an x in it, so it's just a constant. I can factor it out. And integral of x to the 2n is x to the 2n plus 1 like this, divided by 2n plus 1 plus c, right? Indefinite integrals always have a plus c. Again, I need to find c. And again, a very convenient number to plug in is x equals 0, because then in the power series, all the terms with x would just cancel out to 0. Arctan of 0 is 0. And so on the left-hand side, have 0. And then on the right-hand side, all of this goes to 0 because of the x plus c. And therefore, that tells me that c is equal to 0. That's my final answer, arctangent. And the interval convergence is absolute value of x less than 1. For this answer, I don't bother fixing the power of x, because when you have x to the power 2n plus 1, that's telling people that we're taking odd powers of x, and so it's fine as is. All right, next example, let's take a look at 1 over 1 plus 2x quantity squared. How do I relate this to a quantity of this form with derivative and integrals? Well, this is something to the power -1, and then this is something to the power -2. So that reminds me of the formula. The derivative of 1 over x is equal to -1 over x squared. So it looks like if I start here and I take the derivative, I'll end up there. Let's try to see if it works. If I start with 1 over 1 plus 2x, and I take the derivative of it, then I have -1 over 1 plus 2x squared times, by chain rule, the derivative of the inside, so times 2. Great. Then if I divide both sides by -2, then I have, I'm actually going to write this side first. And then divide by -2, I have -1/2 of this side, of this derivative. And this one I can write using the geometric series. Plus 2x, I will write it as minus -2x derivative. All right, so I know what I'll do. I'll start with this, and I'll write the geometric series. And then I take the derivative of it, and then I multiply it by -1/2. That should get me this function. All right, so let's get started with 1 minus -2x. This one is in geometric series form, where the radius of convergence is -2x, absolute value less than 1. All right, let's break this off. The negative breaks off into a -1. The 2x distribute to the nth, x to the nth. The interval convergence. Absolute value of -2x is the same as absolute value of 2x. And I divide both sides by 2, I get absolute value of x is less than 1/2. So that's my interval of convergence. I got this far. Now I want to take the derivative and multiply by -1/2. 1 over 1 plus 2x squared is equal to -1/2 times the derivative of this. Therefore, is equal to -1/2 times the derivative of that sum. Let's just do the derivative separately, and then when we're done, we'll multiply by -1/2. The theorem that we saw earlier allows us to take the derivative term by term. And what about this derivative? That doesn't have an x, so it's a constant. I can factor it out. That doesn't have an x, so it's also a constant. I can factor out. The only derivative is here. Negative 1 to the nth is a constant, factor out. 2 to the nth is a constant, factor out. And then the derivative of x to the nth is n times x to the n minus first. Well, this n minus first here isn't correct for n equals 0. When n equals 0, then the term here is just 1. 0 here, 1. 0 here, 1. 0 here, 1. No x. So when we take the derivative of 1 is just 0. So that term is actually gone. And therefore, the series cannot start at x equals 0. It has to start at x equals 1. Well, I'm actually done, but I'm going to go one extra step, and that is I'm going to shift the index so that my x has x to the power n. I don't like n minus 1. Once you get used to this, you can do it all in one step. I'm going to do it in 2 steps. First, I'm going to do the substitution. Capital N is equal to n minus 1. In that case, little n is capital N plus 1. And when n equals 1, capital N equals 0. And therefore, this series becomes capital N equals 0 to infinity. Negative 1 to the little n is now capital N plus 1. 2 to the little n is now 2 to the capital N plus 1. N little n is now capital N plus 1. And x to the little n minus 1 is now x to the capital N. I'm done shifting the indices, and now I just rename all the capital N as little n. Right. And what is this? This is the derivative of the power series. The function that I want is equal to negative 1/2 times this derivative. And therefore, it is equal to negative 1/2 times this new series. And the interval convergence is, let's go back, where did we find it? We found it here. The interval convergence is absolute value of x less than 1/2. Therefore, that is my answer. All right, let's do one more example and we'll stop. Do we know any way of relating a denominated cube with 1 over 1 minus some quantity y in terms of like derivative or integral or algebra? Well, actually, we do. If we start to, like zoom out a little bit and not think about the details, this is something to the power negative 1. And this is something to power negative 3. And so you know that when you take something power negative 1, you differentiate it once, you get negative 2. And you differentiate again, you get negative 3. So this looks like the double derivative of something. Let's try it. Let's start out with just 1 over 1 minus x. And if I take the derivative of this, then I have negative 1 over 1 minus x quantity squared times the derivative of 1 minus x, which is negative 1 by the chain rule. And that's just positive 1 over 1 minus x squared. If I differentiate it again, this is 1 minus x to the power negative 2. Then I have negative 2 1 minus x to negative 3, so it's a third power in the denominator like that, times the derivative of the inside here, which is negative 1. And the answer is positive 2 over 1 minus x cubed. This is exactly like that, except for this one has an extra 2 and that one has an extra x. So I can use algebra to deal with them, right? Is equal to 2 times 1 minus x cubed. And I want this to look like this. So first of all, I divide by 2, so these cancel. And then I multiply by x. There we go. I have x over 1 minus x quantity cubed. Let's copy it down here. Times the second derivative. I will use this and apply the geometric series. Where the radius of convergence or interval convergence is absolute value of x is less than 1. Okay. First derivative will be, thanks to that theorem, I can integrate term by term, so I can integrate inside the series. I have n x to the n minus first. And because of this n minus first here, now the first term of this was just 1. It's 1 plus x squared, plus etc., right? So the first term of this, when I differentiate, is just 0. So it's gone. Therefore, my series here actually starts at n equals 1. I differentiate again. I differentiate this, sum n equals 1 to infinity of n times n minus 1 times x to the n minus 2. And again, I look at this. What was the terms? When x equals 1, I have 1 times x to the 0, which is just 1, plus 2 times x to the first, which is plus 2x, plus etc. So when I differentiate, this just gone. So I don't have the term n equals 1 anymore. My series starts at n equals 2. So I'm actually done, except that again, I like to have my power of x to be just n and not n minus 2. So I'm going to do a change of variable. Capital N is equal to n minus 2. Then n equals to capital N plus 2. I have an n minus 1. Subtract 1 both sides. N minus 1 is equal to n plus 1. And let's take a look at the limits. When n equals 2, then capital N is equal to 2 minus 2 equals 0. I really should have checked here too. I kind of missed that. Let's do it now. When n equals infinity, then capital N is equal to infinity minus 2, which is also infinity. I should have gotten into the habit of doing that, because even though in this class, almost all the time, the upper limit is still staying infinity, sometimes in more advanced classes, you have things like n that goes backward to negative infinity. So yeah, should have checked that. All right, substitute. N equals 2 is the same as capital N equals 0. Infinity is same infinity. Little n is capital N plus 2. Little n minus 1 is capital N plus 1. And x is still x, and power n minus 2 is now power capital N. I rename the index as little n. And that is my second derivative. My second derivative is equal to this. The interval of convergence is still the same. Absolute value of x is less than 1. And the function I want is x over 2 times the second derivative. And so the function that I want times the second derivative, so it's times all of this. Final answer. All right, let's summarize what we did. If we're given a function f of x, and the first thing we should try is just do algebra, right? But if algebra by itself doesn't help, then try to think about derivatives and integrals of that function as needed to get to the form that we want, which is 1 over 1 minus some quantity y. Once we have that form, then we can write it as geometric series and note down the interval of convergence. And then we reverse from that series back to our original function. So if we have our original function, such as the first example, ln, and we take the derivative of it to get to the form 1 over 1 minus something, then we start from that form. We back up by taking integral to get back to ln term by term. And the reason why we are allowed to do term by term is because of that theorem. And that's why the interval convergence is important. Now, if the process involves taking an integral, then make sure that you write the plus c. And you have to go through the work to find out what plus c is. The two examples that we've had both have plus c equals 0, so that's awesome. But there's no guarantee that c is always going to be 0. Now, sometimes we start with a function f, and instead of integrating it, take the integral of it to get to the form 1 over 1 minus y. It may be easier to start with 1 over 1 minus y, differentiate it to get back to the form of fx that we're given. And don't forget the interval of convergence. Always write it down because that's a condition for us to be able to do all of that integrating and differentiating term by term. All right, hope that helps. Any questions or comments, put it in the comments section below. Like, share, and subscribe for more contents, and thanks for watching. Bye.